Okay, let's do the last two problems on the review, number 11 and 12. It's on that very back page. So let's look at the first one. This one, it's really important that you practice this and understand this because this is the only one on the practice where I ask you to find a rate, but that happens in the homework a few times too, and it might be on the test where I give you the starting amount of something, a different amount sometime later, and from those two numbers and knowing how much time has passed between them, we should be able to find out what the rate of change is. So this thing, let's see what's happening. We're talking about the value of a depreciating car. By the way, this is exactly what you're going to be doing if you choose to do your bonus project. So this is another reason to kind of take a look at this part A here. All right, so we're going to use this model for continuous exponential change, but it's going to be decreasing because my exponent's negative. So we'll have A naught is still the initial amount. That's the price of the car when it was new. So go through and label that. After 3 years, that gives us a value for T right there. The car was worth $15,750. Okay, there's another dollar amount. We only have room for $1 amount over here because the only other variable is the rate, but that's what we're being trying to figure out. So we don't have anything to put in there. So this dollar amount is what this $25,000 became at some later point in time over here after 3 years. So this is going to be your across the equation, like your output of your answer. So let's set this up, but let's fill in all the numbers. So I'm going to do this side first as it makes more sense. Our initial value, $25,000 is what that car was when it was new. Don't forget the E. The E is always there as the base. The exponent is negative rate, which they're calling K this time, times the time. But this time they gave us a value for the time. They said it took 3 years for the $25,000 over here on the right in the formula to shrink down to 15,750. So this is how you set up something where you're trying to solve it for the rate. It's exactly the same setup as if I gave you the rate and I said, how long is it going to take? Where you knew this number, but you didn't know the time value. It's exactly the same steps because both of those pieces of the formula are in exactly the same location within the entire equation. So it's the same number of steps to get something up here by itself. All right, I am going to do this one with algebra instead of with graphing because it gets confusing when I use, in this one, I'd have to use the x-axis to represent rates of change, which are tiny little decimals. And then I would have to rewrite the function and then use the x-axis to represent the number of years. So I don't want to change the x-axis, what it means in each case. So I'm just going to do this with algebra. So I want to solve for k, which is up in the exponent. So our rules say if you're solving for an exponent item up here, you have to first get the base and the exponent isolated, which means anything else that is not part of the base or the exponent needs to be removed from that side of the equation. Since it's a multiplier, we divide. All of these start like this. You always divide your initial amount to the other side. When you do that, it turns out it divides into a nice, pretty little decimal. 0.63 is what that is. I'd just rather use a decimal than carry that fraction. And then this just becomes E. Instead of saying negative K and 3, I'm going to switch the letter and the number around. So I say negative 3K. That just looks like more like what you're used to doing a number times a variable. Okay, but I've isolated my base and my exponent. So this is now where I take a natural logarithm on both sides. So I'll do natural log of 0.63, natural log of E to the negative 3K. What's nice about working in base E is when you get to this step and you apply a natural logarithm, they cancel out. We don't have to do the power rule where we would take that and bring it out in front. So that means on the next line, all I have on the right-hand side is that old exponent, just negative 3K is just a regular expression now. And that's equal to that same logarithm. We haven't really messed with the left-hand side. And so that's it. When we finish, we're just going to divide both sides by negative 3 because I'm solving for K. And that's approximately, if you do this correctly in your calculator, you're going to get 0.154 or something, but it says round to 3 decimal places. So 0.154 is what we're going to use for our rate of depreciation. That means it means it's losing 15.4% of its value each year, but I'm just going to leave it as a decimal so we can use it in the formula. Okay, so I already knew my initial amount was 25,000. The only thing I need to write this model is that K value, and I just figured it out. So I'm going to go ahead and write the model equation here. That's a function that is specific to like this car. So initial value of the car is 25,000. Its losing rate, its depreciation rate is negative 0.154 times T. So this is the function that we're going to use to answer any input and output questions about this car. If I need to know what its value was at any other point in time, I'm going to put it that time unit here and work that out. And that'll give me a dollar amount. If there's a question where they give me a second dollar amount and they want to know what's the T value or how long will it take for this to drop down to a new value, then I'm going to do some solving where I can do that one with graphing. So let's see what they ask us. Part B, find the value of the car after 5 years. So that's the easier one. They just gave us a T value of 5. So they're saying when it says find the value, that's what this is calculating. So we're just going to do A of 5, plug the 5 in where the T is. We already know all the rest of those pieces, times 5, like that. Okay, and then just crank that out on a calculator, and that's going to give us this amount, $11,575 and about 326. So you can use your calculators to practice this and make sure you can put this in and get this out. If I rounded to the nearest dollar, it's just $11,575. So a $25,000 car, losing rate at 15.4% will in 5 years have a value of $11,575. That's what that's saying. So this one was about what was different about this one is having to find the rate instead of finding the time, which we do a lot of times. Like this one, we're going to do it one more time. How many years will it take? Well, that's what we're trying to solve for the T. We could use logarithms or we can do the graphing. But on this one, we knew the time and we're trying to find the rate. So it's the same series of steps, but we're calculating something different. So it's not 0.154 years. It's 0.154 is the rate of depreciation. All right, last problem. We purchased a CD that's a certificate of deposit for $5,000 from a bank that's charging 2.5% interest compounding annually. Actually, I shouldn't say charging, it should be awarding. This is an interest bearing type of situation. So it's awarding or giving you 22.5% interest compounded annually, which is this formula. So there's nothing in this where we have to find an end value. It's very simple. If I can write the formula that's specific to this investment, I need to know how much did I start with and what was the rate. That's all I need to know. So if I can fill in those two numbers right there, the rest of it's just a function notation. So let's do it. A of T equals initial amount. Yep, they told us it was $5,000. 1 plus, did they give us a rate? They sure did, but right now it's as a percentage. As a decimal will be 0.025. Again, if you just can't get that in your head, just take whatever's in front of the percentage and always divide by 100 and it'll show you where the decimal should go. So 0.025, 1 plus R to the T. So there is the model that's specific. I could go ahead and call this part 1.025 just to make it a little easier to work with. Okay, so here they either give us a time that I plug in there and then we work this out to get the dollar amount, or they give us a dollar amount and I either solve or graph to figure out what the T value is. They'll see what the question says. How many years will it take? That means I don't know the T value for it to be worth $6,100. Okay, so I am looking for either on a graph, I'm looking for the point that has a Y value of 6,100, and then I'm going to read off the X value for that same point. Or I could solve it like an equation by putting the 6,100 here. 0.025 to the T, like that. And then just solve it using algebra. So I'll do the graph here in a minute, but I just wanted to, try that again. this turns out to be, when you divide both sides by 5,000, that's 1.22. And then times equals, sorry, just 1.025 dt like that. I'm just going to go ahead and rip through the, I can't stop myself. This would be the logarithm solving by hand method. I have isolated my base and exponent, so now I'm going to go do the take a log on both sides. Because I haven't done one of these in the online review. We did a couple of these in class, but I'm going to solve this algebraically. Get the base and the exponent by itself, so divide the 5,000. Then take a natural log on both sides. Then on the next line, use the power rule to rewrite the variable out in front of the logarithm, or whatever is in the exponent. 2, 5, like that. So the power rule is what allows you to do that. But you can't just move the exponent out in front unless there's a logarithm there. So that's why we put a logarithm there on both sides. And we don't really make any changes to the left, so we just copy it down. And then to finish it, we're just gonna, it's just now the t is a multiplier times some other weird number, some logarithm number. So we just divide that weird number out so that that's what t is gonna be. And on the other side, this is how you're gonna calculate t. 0.025. All right, if instead you want to use the graphing technique, it's a little faster if you can adjust your window. Okay, it's starting at 5,000 and it's growing upwards. So we've got the dollar amounts going up this way, like that. And then this is years down the bottom. And it's asking us, when is it going to equal 6,100? So we're going to find that point right there. We know the output is 6,100. We want to know what that number is. It's the same number if we look at on the graph as what this is going to compute. So let's compute it first so we can prove that it's the same thing either way. So I'll do natural log of 1.22 divided by natural log of 1.025 is approximately 8.053. 6, blah, blah, blah. All right, so I'm just copying that down there. But now let's go to Moodle and let's see if we can do it faster that way. So, not Moodle. I'm tired. I am on the drugs as well, but I'm also, I mean, Zyrtec drugs, not like illegal drugs. Okay. All right, so let's put in the original function. Once we put the numbers in, place it for things like that initial amount. So our starting amount was $5,000. The multiplier is 1.025 to the t. Okay. We can see probably, this is just on some previous window that I had. I don't even know what it is, but this, I'm going to be asking where it's going to be 6,100. So that I can actually tell is going to be on this little chunk of the graph. Go over here and just make it look right. Parentheses like that. Anyway, that's the graph of the value of the CD as it grows over 10 or 15 years here. It's asking when's it going to be 6,100. So just go to the second line because that's an output value. So it's a Y value and type Y equals 6,100. So rather than put it on this side of the equation, just put it in a separate line and then find the point where it crosses the curve. There, look at that, 8.053, something or other. So it is the same number that we got when we did it with algebra, because whichever one makes more sense to you, that's what we can do. So if I go, this is what we just did. I'm just kind of recreating on my paper what I did on Desmos. I graphed the function, this function with the t in it, gave us the curve. It wasn't as curvy as this, but I'm fine with that. And then the specific number that they asked us about, 6,100, you can just type Y equals 6,100 and then tell me what that point is and then answer the question. So the question is, how many years will it take to be worth $6,100? It's going to take this many years. Answer to that question is 8.05, I guess, years. They didn't tell us how to round this time. Okay. But you can get to that either by creating this situation in Desmos, and if you do, just recreate a little thumbnail sketch to show me what you did. Or if you don't like Desmos, you want to just do pencil and paper, then you set it equal to the output we're being asked about, and we go through and do our solving with logarithms. And then when we get to the end, we just type the logarithms into any calculator to get the answer that we're looking for. Okay, so I hope that was enough to help. I'm not doing another one of these, so if this for some reason doesn't have any sound, I don't know. I'm going to try again tomorrow. But let me go ahead and get something uploaded, I hope. So let me stop the recording so I can get on that part of it.